Good evening, ladies and gentlemen. Hello, my name is Paul Davies. I'm director of the Beyond Center for Fundamental Concepts in Science, and we're hosting this evening's events. So a very warm welcome to you all, the operative word being warm. I think Lisa has brought some of the East Coast weather with her. And a special welcome this evening to ASU donors. You know who you are. Thank you very much. Without you, events like this would not be possible. Another special welcome to students. I don't see as many students as I would like, but one or two. You are, of course, the future. And so a special welcome to you, and you're always welcome to come to these Beyond events. Now, the motto of the Beyond Center is confronting the big questions, and we do that through research projects and visitor program and workshops, but we also have a public outreach program. We're very proud of that. And the premier event of the outreach year is the Beyond Annual Lecture, which is what we're having here tonight. And this lecture is designed in a manner that a world-renowned scientist is invited to deliver an address on their specialism, but we also invite them to go a little bit beyond and make some reflective or philosophical remarks about the nature of science itself and maybe their own personal journey. And tonight's lecture is ideally suited to this challenge. Lisa Randall is a theoretical physicist who specializes in particle physics and cosmology. She's Frank J. Baird Jr. Professor of Science at Harvard University and the author of 2 best-selling books, the more recent of which, Knocking at Heaven's Door, is the title of tonight's lecture. Her books are on sale outside this auditorium, and Lisa has graciously agreed to, after the lecture, to go and sign copies for you. Now, according to former President Bill Clinton, reading her latest book, I quote, just might make you think differently. He doesn't say whether it's about him or about the nature of the world in general. I think probably the latter. This book I can recommend as a wonderful introduction to the nature of science and an insight into this wonderful universe that we inhabit. Now, before we begin, could I get you to turn off your cell phones? I haven't done mine yet, but I promise I will do so. Lisa will talk for, she promises, not more than an hour, and then we'll have some Q&A and then the book signing. So, ladies and gentlemen, please welcome the 2013 Beyond Annual Lecturer, Lisa Randall.
Okay, thanks. Okay, I'll start again. Is this too loud now? I get feedback. It's okay with everyone there? Okay. So anyway, what I just said is despite the introduction, it is a lot warmer here. So you guys have no right to talk about being cold. And also, it's interesting that the Beyond is about confronting the big questions, because what I'm going to talk about today is how we, in a sense, how we try to confront these big questions by breaking them down into smaller questions. A lot of the time, people confuse me with other authors. And I'm often asked, like, I work on string theory or the theory of everything. And actually, that's not what I do. What I do is theoretical particle physics, and we try to address questions that we really can address in experiments today. I'm doing theory, but it's theory that we can talk to experimenters and suggest what they can look for, listen to what they're telling us, and figure out how we can actually make progress in what we know about the world. Not guessing about the world, but really what we know, but in the sense of an interaction between theory and experiment. So I have sort of an ambitious agenda tonight. I want to tell you a little bit about how we think about science. Focusing in this book, Knocking on Heaven's Door, it's, the subtitle is complicated, but it says How Physics and Scientific Thinking Illuminate the Universe and the Modern World. And it's because I really wanted to cover two different topics. One is the actual physics that we do, but I also wanted to talk about the nature of science, because I think there's so many different ways people talk about science, there's so many different things people say. And especially at the time I was writing this book, I was kind of disturbed by the things both scientists and non-scientists were saying about what science is and how it works. And we'd like to have a very clean story, but the fact is when we're doing science, in the process of it, things can be messy. But it's messy in a clear way that we can identify. We can identify what we need to do to clear up the confusions, how much better we have to measure things, and what the implications can be. So I want to sort of give you a sense of that story, in particular the notion, which is a scientific concept that I call an effective theory. It's what we call an effective theory, and I'll explain what that is. But sort of how we deal with the fact that we don't know everything. That at any given time we can measure certain things and we can relate certain quantities, and how we make progress in that way. And because I do particle physics, and this was a big year for particle physics, I'll also tell you a little bit about the Large Hadron Collider, which is pretty exciting, although it is shutting down on Thursday for a couple of years, which is disappointing. I read a really funny tweet this morning that's pointed out that the LHC is shutting down the same time, at the same time that the Pope is stepping down. So, so Dan Brown must be very happy. But we are looking forward to the upgrade, but unfortunately it won't be turning back on for a couple of years. So for now, we're going to be going through the data we have. So I'll try to give you a sense of the science that's going on too. And I'll end by just a quick snippet of extracurricular activities. Okay. So I'm going to start with a big question, which I won't answer, because we never do answer the big questions. Will science answer everything? And the fact is, we don't know. And the answer is probably not. There are certain types of questions that science just isn't set out to answer. We'll talk a little bit about the kinds of questions that science does answer. But even within the context of what science sets out to do, there are different types of challenges. And it's important to keep this straight, because science covers a broad variety of fields. And the type of things you do when you're a scientist are really different depending on what kind of science it is you do. I do theoretical particle physics. So in principle, we're trying to find, ironically, the simplest ingredients and the simplest fundamental laws by which they interact. That is to say, we're trying to get to the core of matter, the core of ideas, in such a way that we can define simple fundamental quantities and relate them. When people think of particle physics, when you tell someone you're a particle physicist, they don't think, oh, you do something really simple. But our goal really is to find the most basic fundamental ingredients. And although the steps to get there can be very complicated, what we're looking for are those simple elements. Now, other types of science are putting together ingredients into complex phenomena. Understanding biology or life falls into those categories. Ideally, if you really solve everything, what you'd like to do is be able to understand those complex phenomena and relate it to fundamental quantities. And sometimes we succeed in that in physics. An example that some people might know is thermodynamics, which is the study of heat and engines. And that was eventually understood in terms of atomic physics a century later. So sometimes you can understand these complex phenomena in terms of the simple ingredients. Sometimes we're just happy to understand the complex phenomena. I mean, we'd all be very happy if we can cure cancer, whether or not we know what the fundamental ingredients are. But understanding those fundamental ingredients sometimes helps us. Okay? So they're all different kinds of things. Sometimes it's complicated and sometimes it's complex. No, I think I have to use this. So like I said, I'm often asked about a theory of everything, and I just want to clarify a confusion about what we mean by a theory of everything. Because when people talk about a theory of everything, and I don't, but I'm asked about it a lot, but it's not what I say we're trying to do. But when they're talking about that, they're trying to find the most fundamental ingredients. The idea is that at some point, we'd like to believe that there's some basic theory out of which everything can be derived. Now, even if you knew what that theory was, and even if you knew all those ingredients, you still won't know all the answers. And that's because you don't know the answers on all scales, and you don't know all the implications. Because really understanding a theory of everything would mean that you not only knew what those ingredients were, but you understood all the consequences. And so it's pretty unlikely that we're going to be able to understand all those consequences, even if we have all those ingredients. Understanding string theory, if it turns out to be string theory, if basic elements are strings, is not going to tell you the answer to what the weather is tomorrow. You still would have to understand a lot of other science before you can get the theory of climate. So, and it sounds like an obvious point, but it is something that is often a source of confusion, that you need to put the ingredients together. You need to know the ingredients, but you need to put them together. And which are the right questions and which are the right ingredients can actually depend on the scale. Even if you know the most fundamental ingredients, when you're talking about weather, you're not going to necessarily want to be talking about fundamental strings. You probably are going to want to talk about things that are a lot more practical that you actually have a chance of solving. And another point that leads to a lot of confusion, of course, is the fact that, and I should say that when I wrote my second book, Knocking on Heaven's Door, in fact was an outgrowth of having written my first book, Warped Passages. Because when I wrote that book, even people who were very interested, there were a lot of fundamental confusions about what science is. And in fact, there were even confusions about, in some sense, the reality of what I was talking about, because it seems so far removed from our everyday experience. But the fact is that the fact that it's removed from our experience doesn't make it less real. It just makes it less intuitive to us. Because in many ways, our intuition is guided by the scales that we observe in our daily lives, what we see in our daily lives. And it's important to disentangle those things. So although we see over a very limited range of wavelengths, visible light is from, and we can see things in general, we talk about from, say, a millimeter to a kilometer. The physical universe involves a much bigger range of scales. So before I come back to sort of this more description of how we do science, I just want to spend a moment to actually tour the universe from the largest scales to the smallest scales, to understand what it is that we're learning about, at least from a physics perspective. So we're going to start with large scales. We'll start with the largest scale that we can hope to observe, which is the scale of our universe. Now, some of you might be thinking, isn't the universe infinite in size? And it might be infinite in size. In fact, it probably is. But that doesn't mean we can observe it all. Because the universe, as we know it, has lasted only a finite amount of time, 13.7 billion years, and the speed of light is finite. Which means if we want to look at the universe, we can only see a finite distance. So we can think about this universe theoretically over much larger scales, but in terms of what we can observe, the universe is finite in size. And that size is 10 to the 27th meters. That's 1027 times, okay, multiplied by each other. So it's enormous. Don't forget, a meter is roughly our size. We're all about 1 or 2 meters in size. If there are younger students, maybe they're a meter. Most people here are about 2 meters. And it's not a coincidence that we measure distances in the scales of meters, because that's a very comfortable scale for us. It's like the length of our arm or something like that. So it's a very comfortable scale. But the universe, of course, is 10 to the 27th meters. That means it's 10 multiplied by itself 27 times that big. So it's enormous compared to that. And within that universe, of course, many different sizes. There's galaxies, 10 to 20th meters in size. Solar system, 10 to 13th meters. The Earth, 10 to 7th meters. And then down at the bottom is the human. So what do I want you to think about when you think about that? Well, the fact is, what's so impressive is that the laws of physics work over that wide range of scales. We can use the laws of gravity, the laws of electromagnetism, and they apply over these very, very different size objects. So even though you can see a lot of different structure at all these different scales, the same laws of physics are applying. And I say that because I want you to think about what happens when we look at smaller scales. So now we're going to look at a chart where the person is at the top. So that's the biggest scale we're going to think about in this slide. So now we're going down to to scales smaller than a human size and think about what's there. And I actually start off with a few things from biology because I want you to think about the fact that we actually only know about what's going on even inside a human body because we've actually looked. And that is to say, I really want to emphasize why we look at these small scales. And it's because if we don't look, we won't get it right. So even within the human body, no one understood the circulatory system until bodies were cut open and you saw arteries and veins, see the heart pumping blood. That wasn't understood. No one knew that's what was going on until you actually looked. And similarly, the fact that blood is made up of red blood cells, that was understood when people could look through a microscope and see those blood cells. And DNA was understood when there was X-ray diffraction, so that you can actually see the helical structure. So all of these things that we think of as kind of obvious and we all take for granted now, you don't know about until you actually find them. And much of physics is like that. I mean, we can predict in some cases what should be found. After all, this year we found a Higgs particle that was predicted 50 years ago, and I'll talk later about that. But that was predicted in the context of a lot of other measurements that have been made and a lot of theoretical work that was understood. And without that, no one would make these correct predictions. And I think quantum mechanics is probably the best example of that. No one would have predicted that quantum mechanics was a fundamental description of nature, that the underlying tenets of quantum mechanics were true, unless discoveries were made that just forced it upon people. After all, when people thought about atoms back in the time of the Greeks, I mean, atoms were supposed to be indivisible, unchanging objects. Yet, how do we know about atoms? Well, we can look at their components. That is to say, they are divisible. We see a nucleus surrounded by electrons. And they change with time. That is to say, they emit radiation because electrons change their energy levels. So even those basic ideas of what atoms were not correct. And people would never have guessed that quantum mechanics was the correct description of nature unless it was discovered that there was this nucleus surrounded by electrons, and those electrons didn't fall into the center of an atom and lose energy. They had fixed energy levels. They were quantized. It was forced upon the people who were looking because these observations were made. And I have a lot of technical stuff up there about what's inside matter and what sizes they are. But all you have to see is that at every different scale, you're coming across different elements. And the reason that the grays are different is because whereas before, in some sense, we could think of the same laws of physics as applying quite nicely among those different energy scales, those different distance scales. When you get to the scale of an atom, you really need to use quantum mechanics. Classical mechanics ceases to apply. So in some sense, quantum mechanics is the more fundamental description of nature. It doesn't mean we need to use quantum mechanics on all scales, because the difference can sometimes be too small to measure if you're looking at larger scales or just random systems. Nonetheless, quantum mechanics is the more fundamental description. And you can see that by either looking at the appropriate scales or doing measurements extremely precisely or preparing extremely carefully your system. So it's not that the laws of nature change, but the laws of nature that we find useful change. It's not that classical physics is wrong, it's just that it only applies on certain distances, at which point you have to start using quantum mechanical laws. It only applies at certain speeds, at which point you would have to use relativity if things were going too close to the speed of light. In some sense, there are approximations, but there are approximations that work well enough to send a man to the moon. There are extremely good approximations that are legitimate laws of nature. And it's not that they're wrong, it's just that they're approximations. And so continuing on, we see that today, the frontier energy scale is the Large Hadron Collider. The LHC stands for Large Hadron Collider. Large because it's large. It's 10 to the 27th kilometer in circumference. Sorry, 27 kilometers in circumference. It's not quite that large. It's a hadron collider, that is to say it collides. And what it collides together, from point of view of what we're talking about today, are protons. So from the point of view of what we're talking about today, it could have been called the Large Proton Collider. Protons are an example of a type of particle called hadrons that participate in the strong nuclear force. So that's what we have. And what's happening at that collider is that we're exploring the frontier energy scale, the smallest scale that's ever been explored in experiments. And that's about 10 to the minus 19th meters. So that's 0.0, 18 zeros and a 1. Okay, so it's a really, really small scale. Much smaller than anything you actually can see, much smaller than the scale of visible light. Yet we've developed this technology so that we can understand what's going on at that very small energy scale. And I'll tell you later a lot more about what's going on. For now, I'm going to say that there's still another frontier scale, but that's a frontier scale that we're going to only approach with theory for the foreseeable future. A scale 16 orders of magnitude, even smaller than what we're exploring at this experiment, at the experiments at the Large Hadron Collider today. And that is a scale where even the notion of space itself might break down. So I had a sort of maximum scale, which was, that was not a good idea, was it? A maximum scale, which was the scale of the size of the universe we could observe. In some sense, there might actually be a smaller scale, the scale at which distance, the notion of distance itself ceases to apply. In any case, it's a scale at which quantum mechanics and gravity are both relevant, and we would need what we call a theory of quantum gravity, which could be a string theory. It could be, boy, I'm really not doing very well here. It could be a lot of other things. Well, not a lot of other things, but we're trying to understand what it could be. It's a really tough problem, but it isn't the only problem that we're addressing. Right now, as I said, we're really interested in what we can hope to learn from experiment. And in addition to these questions, there are cosmological questions that we're also thinking about, having to do with dark matter and dark energy. But dark matter in particular, we have some real hope of making progress on. Dark matter, it's matter. It's just like the stuff that we're made of, except it just doesn't interact with light. Really, it should have been called transparent matter, because we can see dark things. Dark things absorb light. So it's not actually dark, it's transparent. It just doesn't interact with light. So a lot of people get confused about the idea that there should be dark matter. They say, we're making it up. But the fact is, I find it more amazing that we should be as large a fraction of matter as we are. There's about 6 times the amount of dark matter as there is of ordinary matter. That's quite remarkable. It could have been anything. It could have been 100 times more. It could have been 100 times less. So the fact that they're so close, I think, is the real mystery. And so in trying to understand what dark matter is, we have some hope that maybe there's a little bit of interaction to explain why dark matter should be so similar in energy to matter we see. So that's all I'm going to say about dark matter. I'm mostly going to concentrate on particle physics for this talk, and also some of the concepts that we're using. So for now, I want you to think about what was kind of remarkable about what I just showed you in 2 slides. I showed you 62 orders of magnitude over which we sort of understand the laws of physics and how they relate to each other, what's going on, how one ingredient builds up from another. We understand the nature of matter in the sense that we understand that this table is made up of atoms and molecules, which are made up in turn of smaller objects. We have nuclei with electrons. Those nuclei are made up of quarks, objects called quarks, held together by a strong nuclear force. It's really quite a remarkable story. Yet, and the whole universe is made up of that stuff, in addition to the dark stuff that we don't yet understand that well. But it's quite a remarkable story that we can put it together. And sometimes it seems overwhelming, and I think we talk about the big questions in the sense of even understanding all of that. I was at a conference once with an English professor who describes sublime as something that's sort of beautiful but scary. And I think in some sense, the universe is like that. It's so beautiful, but there's also so much to understand. And I think that a lot of the conflicts that people have about understanding are because it is a little bit frightening. But it's also something that we can handle. And so as scientists, we try to break it down into questions that we can answer. So we don't just go and attack the big questions head on, usually. We sort of break them down to more approachable questions that we can piece it together and understand what's really happening. So as I said in the beginning, I'm going to try to focus on a notion which we call an effective theory. What is the idea of an effective theory? Well, the idea is that you can't deal with 62 orders of magnitude all at the same time. At any given time, you're doing measurements on a given length scale. And when you're doing those measurements, you want to identify what are the things that are relevant to the measurement you're doing. You don't necessarily need to understand the most fundamental ingredients. You're trying to figure out what are the relationships among things that you can measure. And it's not just a matter of principle, it's a matter of necessity. Because if you don't know things, you don't know them. So if you don't know what those fundamental ingredients are, you can't possibly be describing things in terms of those fundamental ingredients. You're describing them in terms of things that you can actually try to observe and measure and try to figure out what's going on. Okay. So the idea is to keep track of what's relevant to observations and not getting caught up with unnecessary and often unmeasurable details. And you can also use this to identify what you know and what you don't know. Because when you do these, when you come up with relationships among these quantities, they'll usually work up to some level of precision if you got it right. At some point, if you measure things precisely enough, your relationships might break down, and that's a sign that your effective theory is breaking down. It's telling you that you're missing something. It's telling you a clue about those more fundamental ingredients. So it's both practical, it's a matter of necessity, but it also is a real way of making progress. You can understand what's going on at any given length scale and then go beyond it. So this is just an aside, but sometimes, and this relates to this idea of a theory of everything, you don't necessarily have to understand all your complex phenomena in terms of basic elements. I mean, scientists don't always do that at first either. You want to understand the phenomena themselves and then ultimately, hopefully, relate it to more fundamental ingredients. So let's just look at a very simple example, just throwing a ball. Newton derived his laws of motion. You know what happens when you throw a ball. You can figure out where it's going to land. And he did just fine. He didn't know about quantum mechanics or relativity, and he didn't need to, because knowing those things wouldn't have made his prediction any more accurate from the point of view of any measurement he could make at that time, or any measurement about throwing a ball we would make today. You could do just fine doing it. So even though we know that eventually classical physics breaks down because of quantum mechanics, even though we know that if things were going very close to the speed of light, it would break down, at the speeds that they're going when we throw a ball, that's just unmeasurable. It would be a tiny, tiny correction that you would never be able to find. So, and in fact, you don't want to try to use these other theories because you would just get bogged down and never get an answer. You want to use an effective theory because it's effective. It's a useful way. It's a practical way. You don't need to solve everything. You can just use whatever scale is at hand. And that's what we're always doing when we're doing science. And it's a pretty intuitive concept. Google Maps knows this. You know, if you're trying to find your way, I mean, if I was trying to find my way here, I flew here actually, with an hour delay because of the ice and snow, but that's an aside. But if you were coming here and you were driving from somewhere nearby, you wouldn't want to use the map on the left. You'd want to use a map on the right because you don't need all those details. They're not going to help you find it any better if you're coming from Santan Valley. Never heard of it. But if you're coming from there and you wanted to find Phoenix, you'd want to know to take Route 10. You don't really need to know all these details. When you got here, though, if you wanted to find Old Town Scottsdale, well, I guess that would be in Scottsdale. But if you wanted to find something in Phoenix, which I can't really see. But if you wanted to find that, you'd want to use the map on the left. You basically, until you can measure those details, you're not going to use the more detailed map. It won't help you at all. In fact, it would be very confusing. Can you imagine the size of a map that had this much detail in it if you were coming all the way from the Santan Valley? And that's what we're doing in physics, too, or in science in general. You're focusing on what is practical, on what you can do. When you have those more fundamental ingredients, they help you understand your system better. But at any given time, you don't necessarily need to know all those details. And I said earlier that we understand matter, we understand the structure of an atom. We have a tiny nucleus surrounded by electrons. They're not actually in these well-defined planetary orbits, as we know. They're quantum orbitals. Inside the nucleus, we know that there are these objects called quarks, held together by the strong nuclear force. And we understand quite a lot. But it's very easy to forget that there's going to be more. We think we have a theory that works, and we think it's the answer. And when I wrote my first book, I actually went and looked at some of the popular science books because I hadn't actually read many. And I thought I should see what they do. And someone suggested 1, 2, 3 Infinity, George Gamo's book, which was a very good book, but it had this quote in it that I thought was really great because it summarizes both the victory and also the danger. And so if this was back in 1947, so nuclear physics was kind of in its heyday. People understood the nucleus and protons and neutrons. And he said, instead of a rather large number of indivisible atoms of classical physics, we are left with only 3 essentially different entities, protons, electrons, and neutrons. So they understood the makeup of atoms. But then he went on to say, and this is the danger, thus it seems we have actually hit the bottom in our search for the basic elements of which matter is formed, which of course was not the case. Right? That was how much they could measure at that time. That's how much they can understand. And of course now we know that there are quarks inside those nuclei. And so I think today it's very easy to make the same error and think, well, we understand things. Why are we doing these experiments? But of course, it's because that's what we've measured. We haven't been exposed to what could be at smaller scales, what can be going on at a more fundamental level. And that's what we're trying to figure out. So again, I've said this several times, but I'm going to say it a few different ways because I think it's an important point. The ingredients are known up to a point in any given time. But what I don't want to lose track of is that these ingredients are essential, even if they're not essential to the description. Okay? So even if we don't know what they are, these material elements, I mean, science is fundamentally premised on these fundamental ingredients that have fundamental interactions. And I say this to create controversy, but because I do think that it's important to realize that this, I mean, when I was writing this book and trying to describe what the nature of science is, there's a lot of controversy about religion versus science at the time. And I was trying to figure out, really, can you boil down to where this disagreement really is? And I do think this is where it matters. Because I had friends that would say they were spiritual. But then when you try to boil down what that actually meant, they would quickly get confused. Because they'd say, well, I think I have a direction. I'd be like, well, where does that come from? And they say, well, something in my brain. And I'd be like, well, what exactly in your brain? And so the point is that science is really premised on the idea that there are these ingredients, even if we don't understand them. I don't want to say they don't matter, because they do matter. They're essential. An atom wouldn't exist if the nucleus didn't exist, even before we knew about the nucleus. This table doesn't exist if the atoms don't exist. Even if we don't understand it, those fundamental ingredients are important. And it doesn't mean that these things are impossible. But if I'm going to derive a moral sense from something, that is actually some physical process going on in my brain. And the fact that I don't understand what that process is doesn't mean that there isn't a physical process happening. And it doesn't mean that there aren't ingredients there that are making that happen. And that would be what science would say. And so science, I'm going to say, just relies on physical correlates. It doesn't say we necessarily know what they are, but it does say that they have to exist. It says whenever something is happening. And that doesn't just mean that it's in the external world. I mean inside us, inside whatever. It's saying that there's some physical processes that are going on. And it's not even to say that the ingredients in the macroscopic phenomena are necessarily the same. After all, music is more than just the oscillation of air in our ear. So that oscillation of air in our ear is essential for having music, but that doesn't mean they're the same thing. Souffle is different from what it's made of, too. You have all these different ingredients, and you make a souffle. And a souffle really looks nothing like flour. So you can put these ingredients together and get amazing phenomena. And that's what science can tell you. Science can tell you how you can put together all these ingredients to get things that look very different from what you started with. So I just like to think of it in terms of physical correlates. They're not necessarily, you don't necessarily understand everything from basic elements, but they're essential, and we can understand at a higher level. And I think this is all part of the story of what we mean by effective theory and what we mean by doing science and how we build on from one level to another. But science is messy when we're doing it. And it doesn't mean we know all the answers immediately. I did like this Sherlock Holmes quote: "Detection is or ought to be an exact science and should be treated in the same cold and unemotional manner." But the fact is that people do science. And often you'll find scientific results that turn out to be wrong, or things that weren't measured accurately enough, or measurements that get repeated and you get different results. And it's because there are uncertainties when we're doing it. And we saw that, and I think that's the Large Hadron Collider, the story of discovering the Higgs was really a nice story because people saw science in action. They saw an announcement last December where it was indicated that maybe the Higgs boson was found. There were hints of it, but no one was going to say that they really had discovered it because it hadn't met the criteria for discovery. The fact is, there are things that mimic what a Higgs would look like, what this particle would look like. And I'll tell you what this particle is if you don't know, so don't worry about it. But the fact is that there are background events that can mimic it. And what was important for the scientists was to really rigorously show that that they were seeing too much to be explained by just random background. And so, but in the process of doing that, there were stages where people didn't know, was the new particle discovered or wasn't it? But that's okay, because they knew how to go forward. They knew what they needed. They knew they needed more events. They needed more precise methods. And eventually that happened. So today, it's really an exciting time for science. I think we're understanding basic elements of matter, space, and the universe better, in part because of theory, which is what I do, and in part because there really are these measurements that are out there. So I guess I will spend some part of the rest of the lecture telling you a little bit about the science going on today, too. So as I said earlier, the Large Hadron Collider is really the frontier in terms of energy scale, in terms of distances. 10 to the minus 19th meters. It's measuring the smaller distances, the highest energies. It's located in another very beautiful place, not here. It's located near Geneva, also near mountains, near a lake. These are not irrelevant details because when you're building a big tunnel, it actually matters that you're near a lake, because it turns out you have to kind of avoid a lot of the region because otherwise it would be kind of unstable. It's also very hard to drill through mountains. So they were sort of constrained about how big they could build this thing. And they built it kind of big. They built it from almost at the lake to almost to the mountains. And that's how they came up with something that's 27 kilometers in circumference. And that's an important number because the size is important because it determines quite a bit. Because the way these things work is you have protons that go around. And in fact, there's protons that go around in this direction and in that direction. And there are magnets that keep these protons going around in a circle. After all, if there were no magnets, the protons would just go straight. And the magnetic field that you need is bigger the higher the energy of these protons. It's also bigger the smaller circle that you have. If you had a much bigger radius tunnel, a much bigger circumference tunnel, you wouldn't need as strong magnets because they wouldn't have to be bent as much at a given energy. So basically, the constraint of the size of this tunnel and what was accessible in terms of magnetic fields is what determines how high energy this machine can have. It right now is running as what's called 8 TeV, which is in terms of units where E equals mc squared, where we convert mass and energy. It's about 8,000 times the mass of a proton. When it turns back on in a couple of years, it will be at 13 or 14 TeV, so not quite twice as much energy. When it has more energy, we're hoping that it will discover more, but it is a risk because it's not that much more energy. It's about twice as much energy at most. Okay. So eventually, we'd like to see higher energy machines. Those of you who heard of the superconducting super collider, the machine that was going to be built in Texas, that would have had about 40 TeV, almost 3 times this energy of this machine. So it would have had a larger range over which it can see things. And as I've tried to emphasize, unless you look at those energies, you don't see something. From the point of view of a theorist, these energies are all the same. It's what we call the weak scale. It's where particle masses are being determined, et cetera. However, from the point of view of an experiment, a factor of 3 makes a big difference. It could be the difference between seeing particles or not. So far we've discovered one particle, a very important particle that I'll tell you about. It's called the Higgs Boson. But it's not the end of what we'd like to discover, and we'd like to see things happen at higher energies. And there's reasons to think there are other particles that are around there that I'll tell you about. So this is just a really nice video that someone who worked on one of the experiments called the Atlas experiment did, showing the tunnel. This is actually a tunnel you can visit. When the machine turns off at the end of the week, after that, you're going to be able to go visit and walk down this tunnel. And then you can go see up close these amazing experiments that are built around the collision region. These protons collide, then the products into which they collide go out concentrically. And so they have detectors that are built around this collision region. And there's different layers of the detectors that measure different properties. Measure charge, whether it interacts under a strong force, what is the momentum, what is the energy. And it is really impressive. If you find yourself in this area in the next couple of years, I highly recommend that you visit. It's open to the public, and you can't, when the machine is running, not surprisingly, you can't go down into those tunnels. But you will have an opportunity in the next couple of years to go visit. And this is just to show you the end of that, which is just it's going through these various layers. And in this particular video that he did, Zhao did, is going to identify one particular particle. And what this also shows you is that these particles, they do what we call decay. This is a particle called the Z boson. It's like a photon, except it communicates a force called the weak nuclear force. It's actually a massive particle. That is to say, it has a mass. The photon is zero mass. This has a mass at about this weak scale. But it decays. In this case, it decayed into an electron, and it's antiparticle, a positron. So that's actually what the detector records. The detector doesn't directly see a Z boson. It sees these particles that come out. But once you measure everything about those particles, then you can go back and see what was there before. You can determine what was the charge. In this case, the charge is set up to 0. You can determine its mass because you can measure energy and momentum, put it all together. And that's how these experiments work. In general, these particles are not stable, these heavy particles, but you can measure everything about the decay products and try to put it together. Now, you might have seen there was also a lot of other junk in that event. And part of the art of these experiments is distinguishing the good stuff, the stuff you're actually looking for, from the other stuff, which is stuff we know is there because we know about the Standard Model, we know protons are there, we know about the strong nuclear force. There's a lot of stuff that isn't something new. We're looking for these heavy particles that can only be produced here. But in order to do that, experimenters have to distinguish these events from what we call background. And that involves a complicated series of both very clever techniques called triggers to identify what are the things that say, this is something you should keep. It's like a spam filter. It says this is something that's good enough to keep. That's why theorists are important, because we have to tell them the properties that are interesting enough that you'd want to keep the events and not throw them away. But even when you do that, there's a massive amount of data, no pun intended. And basically, there's really impressive computer systems to go through that, a little bit of which I describe in my book. And that's just to say, even though I'm a theorist, I do visit occasionally. So as I've tried to emphasize, the LHC is really important because it really is the frontier machine. It reaches extremes, the highest energy, 7 times higher than the previous machine, which was the Tevatron that's just shut down pretty recently in Illinois. It also has the highest what we call luminosity, which is in some sense a measure of intensity. If you're looking for low probability events, you want to get as many collisions as possible to increase the likelihood of seeing them. It's cold because you have these magnets and they're superconducting so that you can actually afford the electricity to run the thing. And it's the biggest, most effective vacuum. You need a vacuum so that the protons don't randomly scatter, but also to keep those superconducting magnets working. And it has the strongest magnets in industrial scale production. It's actually very impressive. I wish I had a slide here, but these magnets were very impressive because they were built in Europe. And those of you who've driven in Europe know that the roads there aren't quite as nice as they are around here, where they're about 10 miles wide. And you see these really impressive pictures of these 15-meter long magnets going around the roads of Europe. And in fact, one of the reasons for the size of the magnets was that they could actually fit on the roads in Europe. And it's a huge amount of magnetic energy. It was a really impressive operation. And as I said, the reasons for extremes are to get to these high energies and to be able to see events that are low probability. And of course, the experiments, which are independent of the machine, we talk about the Large Hadron Collider machine, and the two major general purpose experiments there, which are ATLAS and CMS. There's two major general purpose experiments. And they're designed to be efficient and as sensitive as they can be, and to measure whatever comes out. Because it would be a shame to make it if you didn't actually record it. So what are we going to learn? Well, one question that we've understood a lot about already is how particles, elementary particles that is, acquire their masses. But there's other questions we want to answer. What explains the weakness of gravity is a big one. Could even involve features of space and time, as I'll talk about very briefly. And also, we might understand something about the nature of dark matter. And as of this summer, a big question was answered because something that we called the Higgs boson was discovered, named after the physicist Peter Higgs. And it really was an amazing discovery that gives some real insights into what we call the standard model of particle physics, which is the theory we know about that describes these basic elements of matter and these interactions, the forces that we now understand. In addition to helping us understand the standard model, this particle is probably a new kind of particle. It's kind of technical, but it's a particle with no spin, a fundamental particle with no spin, possibly. Spin is something that quantum mechanics assigns to particles. It tells you basically a particle acts as if it's rotating, even if it's not really rotating. And most particles we know about, fundamental particles we know about, have spin. A particle like the photon communicates electromagnetism has spin 1. A particle like an electron has spin 1/2. There were actually no fundamental particles seen that have 0 spin. Yet this Higgs boson is a particle that has 0 spin. And if it turns out to be a fundamental particle, it will be the first particle of this kind ever discovered. It's really exciting. And furthermore, measuring the properties of this particle will be the biggest clue that we will have as to what lies beyond, until we actually get to those energies and see what's there. So from my perspective, it was really exciting because we didn't know this particle existed. And in my physics lifetime, the particles that have been discovered were particles we pretty much knew had to be there. In this case, we knew something called the Higgs mechanism was present. The mechanism is the mechanism responsible for elementary particle masses that I'll describe briefly in a moment. But the particle itself was something we didn't know had to be there. It could have been implemented in different ways, and how the Higgs mechanism was implemented would have had very different experimental consequences. So this discovery wasn't something we knew would happen. It was something people expected. There were reasons to think that this particle should exist at around this mass, but we didn't know this for a fact, the same way we did for other particles. Our theories would just have not made sense without it. In this case, we probably could have resolved it. There had to be something, but it didn't have to be the particle that turned out to look exactly the way this one did. So what is the Higgs boson? Well, it's a particle associated with other elementary particles' masses. The reason experimenters knew what to look for was because of this connection to masses. In fact, you know that the Higgs boson is a particle that interacts more with heavier particles, less with lighter ones, which meant you knew how often it should be produced. If it was the simplest implementation, you knew exactly what its interaction should be. If it wasn't the simplest implementation, it would mean you wouldn't find it if you were looking for something with exactly those properties. So by looking for something with exactly those properties, you were testing this hypothesis. Is it the simplest particle that implements this or not? And then the fact that it was found and looked a lot like it is a big deal. Now, as I said, I want to distinguish the mechanism and the particle itself, the boson. It's called a Higgs boson, by the way, because quantum mechanics divides particles into fermions and bosons. Fermions are particles like the electron that has like a spin, half integral spin. Bosons are particles like the photon that spin 1. This is a particle that has spin 0, which is an integer. So we call it the Higgs boson. Now, for it to be the Higgs boson means that it's this particular implementation. So we've measured enough that we know it's very closely associated with the Higgs mechanism. We're still hoping that experiments will measure its properties precisely enough to determine exactly what it is. And that's what we're waiting for, the results of the measurements that are happening now, which we'll probably hear about this spring. But the boson is important because even if it's not exactly what gives the particles their masses, it's sort of an appendage. It's the experimental consequence that tells us it's right. And we know all its properties. We really will know how this Higgs mechanism is implemented. Okay. Now, why is there a mechanism? I mean, this must sound kind of weird, because after all, a mass is something you just say is a fundamental property. Yet, if these elementary particles had masses from the get-go, it turns out you would make nonsensical predictions. You would predict probabilities of interactions that are greater than 1, for example. It turns out they can't just have these masses. There has to be some mechanism. And that mechanism, the only consistent mechanism we know about is this Higgs mechanism, which now we know is in fact correct. And that has to do with something called the Higgs field. And this is really an advanced concept. And I realize it's an advanced concept. It was probably the hardest thing to write in my first book. But we can't help but talk about it because it's there. But it's very unintuitive because it isn't something that you just see in front of you. It's a very different thing. In fact, I wrote, actually my most recent book is a short ebook called Higgs Discovery, the Power of Empty Space, that I wrote after this discovery to explain in a little bit more detail what's going on. But just in a very quick overview, the Higgs mechanism involves something called a Higgs field. Now, a field is sort of a foreign concept in some ways. It's something that's just spread throughout space. But you're familiar with like a magnetic field. I mean, there's not an actual particle between a magnet and the refrigerator, but there's something there. There's a field in between. And in the same way, there's this Higgs field that's spread throughout space. And that's what gives particles their masses. Particles interact with this field. Particles that are heavier interact more. Particles that are lighter interact less. And that's how particles acquire their masses. Now, that isn't actually the particle, but the particle is very closely associated to this field, because if you were to sort of jiggle the field, that is to say add energy to this field, you would actually create this particle, which is called the Higgs boson. That's all fairly abstract, and that really is what's going on, though. There really is this Higgs field. It's what implements the Higgs mechanism. Elementary particles acquire their masses, and the Higgs boson is the consequence. It is the particle. And by studying this Higgs boson, you understand what it is that put that field there in the first place. Where did that field come from? And that's what we're trying to understand by measuring this particle's properties better, to understand where those masses came from. Where did that Higgs mechanism come from? And as I said, the Higgs particle was genuinely new. We didn't know it would be found, and certainly didn't know it would be found as quickly as it was. It could have been heavier, for example, in which case it wouldn't have been seen so quickly. And it could have decayed in ways we didn't anticipate. But with this implementation, experimenters knew where to look, and they found it. And it really was a beautiful example of how science works, because they first found hints of it. It wasn't a strong enough signal. By the summer, they did have a strong enough signal. And right now, they're still studying the different ways in which it decays to see, does that agree with predictions, or is it indication of something deeper and more fundamental? Now, a lot of people ask, where do we go from here? But the Higgs boson is not the end of the story. And part of the reason for that, which, again, I'm trying to put a lot into this talk because I'm excited about it, but I can't explain it all in detail. But there are books that explain it. But basically, we're trying to understand why the Higgs mass is what it is. That is to say, why isn't it enormously heavier? You might say, why should it be? Well, it turns out, according to our theories, if you were to try to calculate what its mass should be, you would expect it to be many orders of magnitude bigger. In fact, 16 orders of magnitude bigger. Something nonsensical. You would have to do this, a fudge, or what we call a fine-tuning, to make it all work. Now, no one believes that's what's going on. It's a really strong clue that there is something else at work. And it turns out that the only resolutions to these problems have to do with exotic concepts, such as new symmetries of nature, or even a new dimension of space, as some of the work that I did with a collaborator showed. So I'm just going to give a very quick hint of how that could happen, how you could explain anything about masses by having an extra dimension of space. And this is going to be even more abstract. I'm not going to go through all of this. I'm just going to say that if you had an extra dimension of space, it could be that the strength of gravity varied as you went from one place to another. Gravity could be really strong in one part of an extra dimension of space. That is to say, beyond the 3 dimensions we see. We know about left, right, forward, backward, up, down. There could be directions in space beyond this. Now you might say, why don't we see them? Well, if light doesn't travel in those dimensions, we literally wouldn't see them. But if gravity was in that dimension, what we found by actually solving the equations of gravity is that gravity could vary in such a way that you could actually understand the nature of particle masses in terms of where you were sitting in an extra dimensional space. Now, of course, that's an awful lot to say in one slide, and I don't expect you to understand it all. But what I do want you to know is that it's not just an abstract idea. It's an idea that has experimental consequences. Because if this is true, there would be particles, they're called Kaluza-Klein particles, after the physicist and mathematician who first thought about extra dimensions of space in the context of our universe. And these particles would have momentum associated with a different direction. Because we don't see that dimension, we would see these as being extra particles that look heavy. And they would have a mass such that they could be produced in principle at this Large Hadron Collider. So in addition to looking for things like studying the Higgs boson better, there are experiments looking for things like this Kaluza-Klein particle, looking for particles that have momentum from an extra dimension. That's a real search that's going on. And when they turn on at higher energies, they will have a much better shot at finding it. So we're looking forward to that. So I just want to remind you that the scale at which you look at things matters. If you look at the Eiffel Tower, you think you know what it looks like, but if you look up close, you'd see the grid work. If you look from far away, you wouldn't know it's there at all. And I like this as a nice metaphor from what's going on in science. So when you look at that, you should remember that it's because you're looking at it from a certain scale that you see it. You should also focus a lot on this, because if you blow that up, you see my name. And that's because I actually was asked by a composer to, after I wrote my first book about these extra dimensions, to work with him in writing a libretto for an opera that premiered at the Pompidou Center. And they actually had this affiche up advertising it. And so, so I will try to see if, I don't know if this is going to work, but I will try to play you a little bit from this to conclude this thing, if I can get this to work. Oh, there we go. I don't know if it's going to work. Well, it was an opera. There was music. And it was about physics and extra dimensions, and it was used as a metaphor. The extra dimension was used as a metaphor for discovery and creativity, but also was used to actually talk about science itself. And the idea was to contrast two characters, one who lived in a 3-dimensional world, space, and the other who explored a 4th dimension, and how they would both understand experiments and observations, but also how they would answer questions. So just remind you that we've gone a long way, but we have a lot to learn. And if you want to learn more, this is the ebook on the right, the other book you can get. But I just want to conclude with one final slide, which I really like, because when I was writing the first book, I thought this would be a great cover, but I wasn't allowed to use it. But it was at the Tate Museum, and I thought it was a really nice metaphor for an extra dimension of space, that you live in this world, you don't know that there's something beyond. And there's this really rich 3-dimensional world lurking in the background. What I didn't know was that was, when I first saw it, was that that's the Chateau de Sion, which is actually very close to CERN, which is where the Large Hadron Collider is located. So clearly not a coincidence. So anyway, thank you very much.
Well, thank you, Lisa. And you would rather moderate your own questions, would you?
I can take some questions.
Okay, but just one plea.
Particularly from the people carrying the
Questions
book.
only, please, not long statements or personal theories. And I have a microphone I can hand around, but the acoustics in this auditorium is good enough. If you speak up, I think we'll hear. So I'll hand over the moderation to you then, Lisa.
Yep. So, you know, this isn't the same as a telescope, where people get telescope time. I mean, the collider has well-defined experimental groups that work on it. And they don't, I say they're looking for my theory, but they're looking for all theories that you can possibly have that might have something interesting. What happens is they take the data, try to identify what could be interesting data, and then break it down into different analysis groups. So in some sense, the experimenters on the experiment are the only ones with access to the actual data, but they will present their results to the world. And if you have a good idea, you can tell them to go look for it, and they will do so.
So to determine among academic researchers who gets access?
You mean they don't look for crackpot theories, if that's what you're asking? No, I'm joking.
University versus, say, an American university?
No, absolutely not. It really is an international thing. In fact, a little-known fact is that we get a very good deal in America because there are actually more American physicists on the experiments than any other single country, even though we didn't build the collider. So we actually contribute quite a lot to the experiments. In fact, I don't know, but I'm sure there's an experimental group here at this university. Yes? Sorry. Oh, okay.
Does the Higgs field establish speed of light? And the reason why I ask the question, as particles approach light, their mass increases. What you said is that the Higgs field is providing the characteristics of mass. What's the relationship between speed of light and the Higgs field?
Okay, so when people talk about the mass increasing with speed, they really are talking about a relativistic mass, which isn't a fundamental mass. The fundamental mass is something that you would have, it's called a rest mass. It's a mass that you would have at zero velocity. That other mass is just something that's a property of relativity. So it has to do with momentum, actually. And so there's a sense in which the energy is increasing because the momentum is increasing, but the rest mass has nothing to do with that. The rest mass is the mass it has at zero velocity. You had a question.
I was curious, how do we know that the Higgs dark matter? For instance, matter might have mass to be dark matter versus actually.
So actually, this is related to an interesting point, which is that there's actually dark matter and dark energy. Now, matter is stuff. It's stuff that clumps. It's stuff that's made up of particles. The Higgs field, if anything, is more like the dark energy because it's, in the sense, it's something that's just spread uniformly throughout space. And it can carry energy, and it can actually contribute to energy. But dark energy is the sum of all the different energies from every field that's around. So it's not necessarily uniquely associated with the Higgs field. So then it becomes a question of what's the dark matter particle, and that can be related. It would have to be associated with some particle that's around, that's stable. Now the Higgs particle isn't stable, it decays. So, but it could be associated with some ingredient that's related to the other question that I talked about, which is why the Higgs mass is what it is. Over there?
I was struck by your quote from Gamov and the blindness to physics.
Speaking of which.
Scales. I wonder about the enthusiasm that the physicists had in the 80s and 90s for everything, and I wonder if that enthusiasm was partly driven by a blindness
Well, you have shown that I am always asked about the theory of everything. There's a big physics community. Some people want, I think what really happens is that people get enthusiastic about the thing they're working on. People thought they had discovered something that unified quantum mechanics and gravity, and they might well have, but it's just a long step from that to understanding everything. And people can be overconfident, mostly men, actually. But then eventually you realize you don't have all the answers, and then you move on.
Just mentioning that when Stephen Hawking gave his inaugural address as Lucasian professor, it was entitled, "Is the End in Sight for Theoretical Physics?" A classic example of what you were just saying.
It's as guilty as everyone. Okay. Yes?
How do we know that dark matter exists?
Well, because dark matter, even though it doesn't interact with light, has gravitational effects. And the gravitational effects have been measured in several different ways. One sort of more direct way is that even though dark matter doesn't itself emit light, matter bends light, energy bends light. So if you had a source of light behind a place where there's dark matter, you would see the light bend around it. And you see it bend in different ways. And then you go back and it would look like there were many different sources because the light had bent in different directions around it. And so you can actually see this lensing effect. So you can almost directly see dark matter. But there are other ways that you can see dark matter. You can see its effect in galaxies on the way on velocity curves of stuff. You think that there's not enough matter around because you see only the light stuff, but you see that the velocities are bigger than you would expect. So you can actually measure what the dark matter should be. Yes?
What does a typical day at work look like?
You get on a plane? No, just it really varies. I mean, I have several different hats, but when we're working on research, I try to find time to talk to collaborators, to sit down and work something out, to write something, to read some stuff. But it's really a mixture. It's a much more collaborative process than people realize. But there's a lot of seminars, there's teaching, I now do public stuff, so there's some of that as well. So it's a real mixture. Sorry.
With the discovery of the massive particle that was first magnitude off of what?
Well, we already knew that it wasn't going to be that heavy. That we didn't need to actually discover it. It couldn't have been that heavy in some ways for other reasons, but I can talk about that later.
And then if that particle is emitted, like the field.
What we really do is just collide together particles. This is more of the theoretical interpretation of what's going on. But what we're doing is colliding, or what they're doing is colliding particles.
Is there any possibility that dark matter, like an interface zone, this reality and another, as though it were a lace on this side and another one on this side, touching each other?
Well, we kind of know enough about dark matter properties that it probably is just matter. I mean, it really looks like it's matter. I don't even know what that would mean, really, but I do know what matter is, so I can test, does it agree with the properties we would have? And probably one of the best ways that you can really see dark matter is there's something called the bullet cluster. So you just have these the colliding cluster of galaxies. And you can actually measure from lensing, the effect we talked about earlier, that some stuff goes through where some stuff gets stuck in the center. So the gas gets stuck in the center because it interacts, and the other stuff goes through, and that's dark matter. So it's hard to see how esoteric theory like that could be consistent with something as concrete as that kind of measurement. Yeah.
You mentioned earlier that they're hoping to find out why gravity collider. Are scientists hoping that they'd be able to pin it down to gravity rather than forces know it, but brought down to a central particle out of the atom, which causes all of the gravitation from the atom?
Well, no, because we know, for example, there's dark matter, which has nothing to do with atoms. So it really is an independent force. And it's just there's matter within that theory that experiences gravity. In the back there?
So just two more questions.
Okay, good. In the back over there? Other dimensions, what? It's actually really hard to make a consistent theory with extra dimensions of time. We know that we can make dimensions of space. As to say, we know that dimensions of space consist and at least be consistent. For them to be consistent with measurements, they have to have certain properties, and we know how to do that. In the case of time, if there are extra dimensions, not surprisingly, things just don't make sense. It's easy at just a laughable level to sort of talk about why they don't make sense, but it turns out things are unstable. It's just no one has really made a sensible theory where you really have two dimensions of time. Okay. Sorry. Okay, you both. There's two more questions, and that's it. Okay. Okay. All right. So first of all, it's always useful to think in terms of effective theories, because what we call a particle today could turn out to be not a fundamental particle tomorrow, because we could find out it has more fundamental ingredients. But what I'm calling a particle is this. I think what you're asking is something that has definite mass. A mass is a relationship that, for any given energy, it has a certain momentum. Well, you know about E equals mc squared. But really, there's a slightly more complicated formula that involves both energy and momentum. That's always true. And that the particle mass is a fundamental property of that particle at that level. Okay, last question.
Comment on particle movement excess.
Yeah, I'm done. We don't have any sensible theory where particles go faster than the speed of light. It just doesn't make sense. I mean, basically our notions of physics would break down because our notions of causality would break down. So we really don't know how it would be such a fundamental restructuring. It just doesn't make any sense at this level.
Okay, thank you. Thank you very much, Lisa. Now, look, before you all rush for the books, a couple of announcements. First of all, our next event on the Beyond Centre calendar is Ian McEwan, who this will be a very different type of event. Ian is a world-famous novelist who writes not exactly science fiction, but fiction about scientists. And I think if I remember the date correctly, it's March the 28th, Ian McEwan in Conversation. So make a note of that. Then the final thing is that these events take a lot of organizing. And Adriana Fontes, my assistant, who's usually around here somewhere, is in charge of all that, and she tells me exactly what to do. And she has with her a group of student helpers, and there's Adriana at the back, I think. And that includes Katie and Rosella and Gia and John. And Gia's the one with the flower in her hair. You'll probably remember that. So a special thank you then to all of the helpers who made this such a successful event. So those of you who want to buy books, please form an orderly queue outside. Those of you who don't, then feel free to leave by the side exits and be sure to drive carefully. Thank you.